landing will be there. Landing, then again you start climbing like this. Okay. So this is a in elevation. In elevation, if you try to see this one, it looks like it looks like a, this is a floor level at the ground. Steps will run like this. You're reaching the landing here. Then the next flight starts here. Second flight starts like this. Okay, I'll not show that entire diagram. This is the first flight here. So when you reach the landing, vertically you have moved 50% of the total height. That is standard ideal design it is. So at the end of the first flight, vertically you have traveled by distance which is equal to half of the total height. See, when you climb the remaining second flight, when you climb the second flight, again you are moving vertically up by the remaining 50% of the total height. So in the examination, you are supposed to design any one of this flight. Any one of this flight, preferably the second flight is designed. Flight number 1 is this. It starts from the ground floor level to this landing level. So we call it as a flight number 1. This is F1. So from ground to landing is flight number 1. From landing to the next floor is second flight, flight number 2. So in short, we can say it is like this. In short, this is ground floor. This is first floor. From ground floor to first floor to reach, you have to cross 2 flights. One flight is like this. Second flight is like this. I think you are understanding already. This is there in geometrical design, was there in the previous semester only. But even then, geometrical design is only one step in this particular. Like this, you are going to go here. Finally, you will reach this one. Okay. So this is the total height, vertical height traveled. Total height of the from ground floor to the ceiling, bottom part is ceiling. We call it as bottom part of the slab is ceiling. That is why we call ceiling fans. Ceiling fan means a fan which is attached to the ceiling. Okay. So now usually whenever a problem is given, whenever a problem is given in the examination, usually flight 2 has to be designed. Flight 1 design is little bit different. Flight 2 has to be designed. First, let us understand how to design the flight 2, then you can think of flight 1. So this is the one that is flight 2, this is flight 1. From ground to landing, flight 1. From landing to first floor, this is flight 2. So how to design flight 2, let us see first. So to start with, we have to geometrical design means like this. It is only the room dimension is given. From the room dimension, I need to finalize all this. What is the landing width? All these dimensions you have to finalize. Which are those dimensions? So what will be this dimension? What will be this dimension? Usually both are same. And what will be the width of the flight? This width of the flight is this. Whatever I'm showing here, usually both the flights are of same width. In order to maintain aesthetics and symmetry, width of this flight number one or flight 1 and 2, width should be same. Preferably the landing should be same. For example, if this width of the flight here is, let us say this is y and this is x. Usually x and y are same. So the width of this landing and width of the flight are kept same. And the number of steps in the flight number 1 is usually equal to number of flights, number of steps in the flight number F2. For symmetry it is done, but in some cases there can be more number of steps in flight 1 than flight 2. That can also be designed. Design remains same even if the number of steps are different in the flights. The design will not change. Now you can see this. So step number 1, when I say, see this one. Geometrical design and effective span is step number 1. In the today's class, I can only cover this much. Only step 1 can be explained in today's class, which is already done in your building construction subject. So in the step number 1, what we are going to do is we are going to plan the geometrical design. Means how many steps will be there, what is the size of each step, how much I should leave this side, beginning of the step, how much is this distance I should leave, how much is the landing, how much is the width of the stair, how many steps I can accommodate, what will be the size of each step. This is all comes in the step number 1 only. Okay. Now let us come to step. One step is like this. Next step is like this. And these steps are supported on a slab. This is the slab now. This is the slab. So slab is this. Reinforcement is there inside now, inside the slab. Weight of the steps must be calculated and weight of the step is also transferred to the slab. Slab is supported at the ends. Slab has to be supported here. Now how is the slab? I'll show you. Observe this. How will be the slab? Second flight. So this is the slab now. This will be the slab. Entire slab. It is in this shape, Z shape. Whatever I have shown, no? Z type it is. This is the slab here. We have to design this slab, and whatever is the load of steps coming and whatever people climbing on live load. So live load and dead load of the steps, dead load of this slab should be considered to design. Usually it is supported on the beams. Here there will be one beam, there will be a beam here or a wall will be there. Ultimately the slab has to be supported on the columns, on the beams there. Beams in turn they are supported on columns. Okay, if you want I'll show you that. You want to see this one. Now this Z shaped, I'll just try to hatch it. I'll hatch it. Observe this. Whatever I'm hatching, that is the slab actually. This one, and this one. Z shaped. This is all your slab to be designed. Equivalent, it is taken as horizontal only. How it is done, I'll show you. And this is one beam is there, which the slab is supported. At the other end also, one more beam is there. See, these two beams are in turn supported on columns. How it is, you can see here. How it is. how it is done, you can see. There is one column here, one more column here. Consider the ideal situation like this. Okay. Now a beam runs here like this. A beam runs here like this. Now this slab, first flight, whatever I have shown here. Now these are the four columns. You can see this. This slab, which is in Z shape like this, it is supported on this beam. I'll call this as, let us say, I'll call this as beam B2, this as B1. So this is the beam B2 now. This one, this is beam B2, this one. And this beam, there are two beams now, but you can see in plan only one. This is B1. So this B1 is running at what I can say landing level. That I'll show you again. Just observe this figure. Landing level. That is, step starts like this. It goes like this. Again, steps start for the next flight. It goes like this. Now I'm going to design. I'm going to design here. Okay. Now you look at these diagrams, top and bottom, both the diagrams you see there. B1 is here. Then you look at this one here, B2 is here. This is B2, whatever I have shown in plan, that comes here. B1 comes here now. Okay. Now I'm going to design a slab which is this shaped, which is supported on B1 here, B2 here. You can call B1 this side, B2, there is no problem, but I'm showing you how it is structurally loaded. You should understand that the slab has to be finally supported on beams. Beam has to be supported on columns. See this. This B2 is supported on these two columns. This B1 is supported on these two columns. So how the load transfer is taking place? So the load from this inclined part of the slab staircase with steps on it, plus this landing, plus this side landing. This side landing. Two landings are there for F2. For F1, only one landing is there because it is ground floor. For first flight, there is no two landings will not be there. Imagine in our college, all staircases are dogleg staircase only. All are like this only. You go to anywhere, any corner of this, it is all dogleg staircase only everywhere. So here, so let us see how to design this part. Now, how the loads are there? Observe here. In this landing number, let us say L2. This is L2, horizontal part of the slab. L1 is this landing, again horizontal part of the slab. Then this one is inclined portion of the staircase. So the staircase slab consists of one horizontal portion L1, one inclined portion, and one more horizontal landing portion L1. So I can say L2, this is L1. Let us say L1, what are the loads here? On this L1, the loads are live load plus dead load of this landing slab. What are the loads on this inclined portion of the staircase slab? We call it as a waste slab, WAIST. Waste slab it is also called as. So waste slab, one landing slab, one more landing slab, together it forms a staircase slab. Okay. Now on waste slab, what are the loads? Dead load of the waste slab itself, dead load of the steps, live load of the people climbing on this part. So there are three types of loads I can say here. One is dead load of the slab, dead load of the steps, live load. Here there are no steps, there is only live load of the people moving around and dead load of the slab. Here also dead load of the slab, people moving on this landing part. It means this inclined portion has three different types of loadings which we have to calculate and add them. Finally, how this L2 and waste slab and L1, how it gets converted. Equivalent horizontal slab it becomes like this. This is the support here. Dotted line I will take. One support is here. One more support. It becomes a simply supported slab now. It is converted into a simple problem. Then this landing wherever it ends, here, this much actually I have shown in the figure is not properly represented, but this part will be more. Inclined steps part will be more than this, like this. The middle portion will be more actually. So this load is shown like this. Dead load of the slab plus live load of the slab together it is. Then one extra is shown here, because in this portion of the incline, this dotted lines are taken. This portion is inclined portion, equivalent horizontal line is drawn here. It means in this portion load is more because of steps are more. Steps are there. Steps, dead load plus live load it is. That is why if this portion is more. Actually, the diagram is not exactly representing that one, but actually it is. This length will be more than landing this side, landing this side. That you will come to know while solving the problem. So step number one, I think step number one is all about just finalizing the plan of the staircase with steps, riser and now when I show a step separately, can you name this one? This one is what? This one is what? Usually standard dimensions of rise, depending upon the size of human leg it is. So this is 250, this is 150. You can change them slightly, but slightly it's very close to these two dimensions. For a residential building, this should be 250, this should be 150. Okay, what are the names for this one? What do you call this one? This side horizontal, what do you call it as? Now I'll tell you what it is. This entire thing where steps are there in the plan, we call it as going. This is landing. Now if you take the second flight, this is going, this is landing, this is one more landing, because in the second flight I am designing now. This entire thing is called as going. You have to calculate the going after finalizing the steps, how many steps are there and all. Okay. So this is riser or a rise. This is capital R. R is 150. T capital is 250. Tread. Okay. Step is TREAD. Tread 250. Rise 150. You start with these dimensions. There may be slight changes in the dimensions to adjust for the half of the height. First flight vertical height, to adjust that one, there will be slight changes in 150, may become 146, something like that. But you should start with these two step dimensions. Okay. So let us see the step number one after this. If any doubts are there, you can ask. I'm going to do only the geometrical design. Another 10 minutes, I'll stop it. Today, I'm going to stop after 10 minutes. So you can see the step number 1 is geometrical design. I think I'm not able to load this one here. Anyway, page number 9. Whether it is here or here, I need to check. This is of 7th semester. See, all of you just type your USN. Don't type both. Huh? In the text, type just USN. USN and one space, then division A or B. USN space A or B. So it is getting downloaded actually. A division, division A. Simran 98. You give your attendance. Daneshwari 25. You can unmute and can give the attendance. Yes, it has opened now. See. Let us see the geometrical design here. See this one, I have already explained some of it. Design a dog-legged staircase for an office building in a hall measuring 3 meter by 6 meter. Inside dimensions are 3 meter by 6 meter. Vertical distance between floor is 3.6 meter. So vertically, I have to provide 2 flights so that vertical distance covered will be 3.6 meter from ground floor to first floor or second floor to third floor. 3.6 meter. Public building is liable to overcrowd. Means live load should be 5 kN per meter square. Landing slab spans in the same direction as flights. It means the direction of landing slab and flight is same. Supported on walls of thickness 230 mm. There is a wall here, there is a wall here. It is supported like this. You can see this diagram here. Z-shaped, something like this. You can see this. Actually, it looks like a leg of a dog. That is why it is dog-legged. Looks something like a dog-legged staircase. It is called as because of that reason. Supported on walls of thickness 230. Use M20 FA over 1. Step number 1 is geometrical design. So what I have taken here is, since the dimension is, since the dimension is 3 meter. See this. One of the dimension is 3 meter. Out of that, I have left some space here, 300 mm. Usually it is 100 mm for residential. It can be anything. I have taken it as 0.3 meter. You can use 0.2 also. The dimensions will be more here. Flight width will be more. So what I have taken is, I started with what is the gap inside. Start with this middle gap. It is 0.1 to 0.3. For public building, it is little bit more, 0.3 it is. So what I have done is, total inside dimension is 3 meter. 3 meter by 6 meters. This one is given to me. 3 meter by 6 meter hall is given to me. I started with this gap without worrying about anything else. What should be this gap? Whether gap should be given or not given, in some of the residential buildings, gap is not there. So this gap is preferable, 0.1 to 0.3. I used 0.3 as the gap. Once it is 0.3, I can, out of 3 meter, 0.3 is gone, remaining by 2 this side, by 2 this side. This is 1.35. So it is 1.35 plus 1.35 plus 0.3. It is 3 meters inside dimensions. Okay. So when you start planning, geometrical planning design, you should start with the gap. How much should be the gap? Then only you can finalize the remaining. You must see that it should not be less than 1 meter at any cost. Preferable is 1.5. If at all the dimension was 3.5 meter, I would have adjusted that one. Now here 0.3 I have taken. You can very well take 0.2 meter here. Nobody will object. The design slightly changes, that's all. So now this is 1.35, this is 1.35. What I have done here is, since this width of the flight is 1.35, the ideal case is this should also be 1.35. I have taken just to make it symmetrical, that's all. No other idea. I know that this is 1.35 because the gap was considered as 0.3. Once this is 1.35, this is also width of the landing is also taken. There is no hard and fast rule for this. But it should not be less than 0.3 again, 0.9. Preferably it has to cross 1 meter. Best is 1.5 here actually. But since I am having 1.35, I am using this also 1.35. This is all designer's choice of the designer, all these things. But it should not be impractical also. 0.8 or 0.9, if people cannot cross, while crossing there should be minimum 3 feet, which is 1 meter for residential buildings. Now 1.35 is okay. Anything above 1.35 means 1.5 would have been better. But right now we cannot do that in this case because width is 3 meter. Okay, this is how this is done. Now what I have done is I started with 0.3. I got this 1.35, this 1.35, this is 0.3. Then I used 1.35 here, this side. Second flight. This side also I am leaving 1.35. Then I'll calculate the remaining out of 6 meter. 6 minus 2 into 1.35. I am going to get what is called as going. How I got going here? The going was obtained. This was obtained. I'll get it later actually. I have to fix. In order to get this one, I should go further, decide the step dimensions. Let us say I have decided 1.35 and 1.35. Horizontal space between two flights. Okay. Horizontal space between two flights is 0.3 meter. This one. Okay. It's 0.3 meter. 3 minus 2 into 1.35. Floor to floor height is 3.6 meter given. Height of each flight is 3.6 by 2. Height of each flight is this distance. I'll just draw this one, observe. Height of each flight. This. How to calculate this? Total height divided by 2. Total height is given in the problem. Floor to floor height is given. 3.6 by 2 is 1.8. So start with, assume rise as 150, tread as 300. Why it is 300, not 250? Because it is a residential, it is a commercial building. So for commercial building, it should be 300. Rise can be same, 150. Comfortable, this one is 150. 115 is 6 inches. This is 12 inches. Usually, if you try to understand in inch mode, 6 and 12. This is 6 inch, this is 12 inch. So 300. Now number of risers. See this. Number of risers in each flight is height of one flight divided by height of one step. Height of the flight by height of the step. That is That is, see this 1.8 by 0.15. 12 numbers. Number of risers is 12. If I provide 12 risers of each 150, I will be reaching 50% of the total height, which is 1.8 meter. It means if I provide 12 risers, 150, again 150, again 150, like that, 12 risers if I provide, I will be climbing a vertical height of 1.8 meter. So next is, so number of treads is 1 minus this. Always number of treads will be 1 less than number of risers. 12 minus 1 is 11. Now I am getting going. Going is what I told you here is this. This is going, because once I know that there are 11 treads, number of treads are 11 into 300. 300 means each step width. So this is total, I am getting 11 treads, 11 into 300. Total is 11. 11 into 300 is 3.3 meter. It means I got this distance as 3.3 meter. 3.3, and we have to add those two. Okay. So landing on each side, I'm getting landing on each side like this. Total is 6 minus going, middle portion, by 2. So 1. Good afternoon, all of you. So let us continue the design of staircase. So we'll start with once again the steps involved in the design of a dog-legged staircase. As you know, here it is first of all geometrical design should be carried out. You can see this one here. Geometrical design followed by the effective span we should calculate. Second step is effective depth and load calculations. So usually load calculation will take more time in case of staircases. Once the load is calculated, loading diagram, PMD and SFD, check for the depth. So once you calculate the bending moment, factored bending moment is compared with MU limit again. MU limit has to be more than bending moment. Finally, reinforcement. Mean steel and distribution reinforcement, development length, check for deflection, sketch the details. As I already told you, shear checking is not required, but if it is asked in the examination, simply find tau c into BD, that's all. Find out tau c BD, then check that value with VU. VU will be always less than tau c BD, so no stirrups are required for slabs. So let us go to this step here. I already told you that, see, when geometrical design means you should know, you should have some knowledge about the dimensions of a step. Always this is 150 in most of the cases. This is 300 or 250 depending upon whether it is commercial building or a residential building. So tread is usually 250 for commercial residential structures. For commercial buildings, the tread means this horizontal part of the step is 300. So once you know this one, you should be able to decide this. See, for example, in order to geometrically design, how many steps will be there? As I told you, this is you can see this is divided into 3 parts here. One is Usually the intermediate flight is designed, not the ground flight. I'll tell you what is the reason why I should usually design. Now you can see this. So whatever I am showing here, you can see this one here. What I'm trying to show here is, so I'm going to design intermediate flight. This is intermediate flight. This is the first flight of the ground floor. Now, how the ground floor slab, that is, this is a slab you can see here. Inclined slab is there like this. Landing is horizontal. In between, it is a waist slab. WAIST. So it consists of landing and waist slabs. Now here, if it is uh, first flight from the ground floor, the diagram will be slightly different like this. It can be like this also. If you have seen in the textbooks, it can be like this also. Because no, this one is required here. This landing is not required when you start from the ground to the first landing. That is for first flight, which starts from the ground. The structure will be something like this. Simply it is like this is all already there. No need for this one. In some cases they may have the landing also, which is rare case. Whatever I showed in the red color, directly it is like this. That is why they usually tell you to design an intermediate flight. So an intermediate flight is, you can say, second flight of from ground to second flight, or any other flight. When you try to go up to the second floor, this type of a situation will not be there. So what you need to understand here is the ground floor first flight, which starts from the ground floor. The support system is like this. The slab has to be supported on a small column and a footing like this. Otherwise, I cannot support it directly on the ground. I cannot support the slab like this. So this slab ends on a column here, small column it will be, maybe 1 meter deep. Then footing will be there below. Column and footing is next module actually. But this is how it is arranged when the staircase starts from the ground. Okay. So normally what they are doing, they are asking you to design intermediate flight. So this flight, if I design, it is common for all other flights. Even if it is a 10-story building, this remains same. This design remains same. Okay. So once I say intermediate, now if you want to climb to the next floor, second floor, third floor, all those both the flights will have the same design like this. Now we can see this. Finally, I need to get a loading diagram like this. It means the inclined portion has to be converted into equivalent horizontal span like this. Then this is you see this is one landing here because it is intermediate flight. This is one landing that is shown at the top like this. The other side, this is the landing that is shown here. The inclined portion, you can see the dotted lines. The inclined as waist slab is converted into equivalent horizontal line like this. Okay. So this is what is done and loads are calculated. That is the next step actually. So this is what you need to understand here. See, when you open any textbook, they might have designed this also as well as this also. Once I design this one, which is more time consuming than this will be very easy for you. This will be easy. That's why I'm taking intermediate flight, which has two landings. Okay, ground floor has only one landing here. If the flight starts from the ground floor, it has only one landing. So I'm going to design an intermediate flight which has two landings, this side as well as this side. Let us see this one here. So what I have done here is, I started with the room dimension was given. I started with the gap here. It is 0.1 to 0.3 meter. Okay. If it is usually for commercial building, this gap is more. So like this, I have calculated here. How to calculate? Once again, you observe here. So once this is fixed, once this is fixed, what I have done is total in this one, that is 3 meter. I have subtracted 0.3. 3 minus 0.3 by 2. That is 1.35. I got it. So horizontal space between the flights is taken. Floor to floor height was 3.6 meter given in the problem. Height of each flight. Each flight has a height of 3.6 by 2. So after getting the vertical height of each flight, there will be two flights. I need to find out the number of risers and all. So for that one, what I will do? Height of each flight divided by one riser height. One riser. So 1.8 divided by 0.15. So 12 it is. Number of treads will be 1 minus this. 12 minus 1. From this one I can get going distance. So 11 into 300 is taken. So I am able to find, you can see this distance. I got this distance. So 11 into 300. 300 is tread. So 11 treads are there. 11 into 300. So it is 3.3. So once I find out this one in total 6 meters, because since this width of the flight was taken as 1.35, I'm going to fix this also as 1.35. Now I'm having 3.3 and 1.35. This is also I have taken as 1.35. In 6 meter, you subtract 3.3 and 1.35, you are going to get this distance, this side distance, which is again same in this problem. It can be different also slightly. This is also 1.35 only, we got it. So that is why geometrical design has to be done properly here. You have to remember one thing here, 150 and 250 dimension. This is 150, this is 250 if it is residential building. Otherwise it is 300. So like this, all the dimensions are fixed. Now I'm going to find out effective span. What is the effective span of the staircase? How to get it? Now you can see effective span, how to get this one. I'll draw this figure. What is exactly is effective span? Observe this figure. This is the intermediate. Okay. Now what is effective span? Horizontal distance it is. These are the supports, or they can be columns. It can be a wall or a column. The thickness is given in the problem as 230 mm. Now what I will do, what is effective span here is, effective span is the horizontal distance. Center of this support to center of this. This is effective span. I need to calculate this now. Okay. How to calculate it? Now it is not difficult here. Just observe. So this is what is called as center of this to center of this. So this much is effective span for bending moment calculations. I am going to consider this as L effective. L effective. So let us see how to calculate it, because this is a part of the first step. Now what I have done is, see this one. So I have calculated landing on each side 6.6 minus 3.3 by 2. So the landing is adjusted equally. Either you fix a 1.35 if you assume width of the landing is 1.35, width of the flight. This is width of the flight. Again, observe this. This one is width of the flight, and this is horizontal. This is width of the landing. Okay. So this is vertical line is width of the flight. Horizontal green line is width of the landing. So either you fix this is 1.35 equal to this is also width of the landing also 1.35, or one more method is you subtract this. See, this is total is 6 meter. Total is 6 meter. You subtract this much 3.3. Whatever is left, distribute equally on either side. So it is 6 minus 3.3 divided by 2. Because I have to distribute that distance this side equally. But even then you are getting 1.35 only this side also in this problem. So like that it is done here. That is 6 minus 3.35 by 2. It is 1.35 on either side. Okay, on either side the landing width is 1.35. What it means? It means red color line, this is also 1.35. Green color horizontal line is also 1.35. Now let us find out the span. Now I'll start from 0.23 by 2. 0.23 by 2 plus 1.35 plus 3.3, again 1.35 plus 0.23 by 2. Now observe this, what this calculation is. Half of the thickness. Now see this one. What is 0.23 by 2? This much is 0.23 by 2. This is 1.35. Again this is 3.3 going. Again 1.35. Again 0.35, 23 by 2. Is it clear this one? This is 0.23 by 2 half. Then go inside by landing 1.35. Again add 3.3 this distance. Again 1.35. Again add half of 0.23. So it is 2 times 0.23 by 2. 0.23 by 2 here. This side 0.23 by 2. 2 into 0.23 by 2. Again 2 into 1.35, because just see this one. What is happening here is, what happens here is, see this is 0.23 by 2. This side also 0.23 by 2. This is 1.35. This is 1.35. This is 3.3. So what I can do here is simply I can write 2 into 0.23. You can see this one by 2. And covering this half as well as this half now. Okay. Plus 1.35 and covering 2 into 1.35 means this landing as well as this landing, plus middle going, we call it as, that is waist slab, horizontal distance of waist slab. This is inclined, this is horizontal. Like this you can calculate it. So this is L effective. L effective will be this. Any questions here? Any doubts? How I calculated L effective is like this. This is what is done here. If I go to the, I'll not go to the previous page. I'll just show you this one only. I'll enlarge it. Okay. Now this is a, see, 0.23. This is 0.23 by 2. Any questions are there? You can ask. This is 0.23 by 2. This side. Again, this side 0.23 by 2 here. This side. So 2 into 0.23 by 2. This is 1.35. This is also 1.35 landing. So 2 into 1.35. Okay. One more method that you can follow if you are not this one comfortable with this is simply what you do. Start from this 1.35 plus 3.3, again 1.35. Add one thickness. Add one thickness. That is, add just 0.23. That will be, if you want, you can do like that. 0.23. This is 0.23. Is it clear this one? Second method is 5 minutes. 5 minutes here. See the second method you can see here. 1.35 plus 3.3 plus 1.35. Just add one thickness. One thickness is 0.23, which is same as this. But for understanding purpose, I have explained like this. You should know how to calculate the effective span. So this will be L effective for calculation of bending moment. Now this distance, see this. Now when you draw this line, when you draw this horizontal line here, horizontal span has to be shown. How to draw that? Observe. I'll show it here. I'll show it here. Last page is there, but once again you see here. So these are the supports here. Okay. So I'm having a span of, I got a span of 6.23. So this is 6.23 overall 6.23. In that one middle portion, what I will do, 3.3 middle portion I'll mark it. This is 3.3 middle portion. So this distance is important. You are likely to commit mistake here. How much will be this distance? This one. How much will be this one? Loading and all I'll calculate. I'll tell you that one. So once the effective span is calculated, which is 6.23, how I got this one is by this formula. If you calculate this one, it will be 6.23. So in the horizontal span, I have to distribute it, not in this inclined way. So I should make an equivalent horizontal slab now. So 3.3 is this, okay. Out of 6.23, out of 6.23, you observe here, how much will be this? This is a landing plus 0.23 by 2. This is important here. It is not simple landing here. I'll write it, observe this one. This distance is, this will be, how much is this distance? And this one, this will be 1.35 landing plus 0.23 by 2. Half of this, because it has gone 50% inside. Okay. Support is at the midpoint of the wall or column. So this will be 1.35 plus half of the thickness, whatever thickness is given, which is 0.23. So 1.35 plus 0.23 by 2 here. Here also 1.35 plus 0.23 by 2. Okay. That is what is shown in the diagram here. You can see it is 1.465. This side 1.465. This side 3.3. In the middle, going is 3.3. It is landing plus half of wall thickness or half of support thickness. Again, this side also width of the landing, that is 1.35 plus 0.23 by 2. So let us see how to calculate the loads here. Loads must be calculated on horizontal span. So how to do this? Observe this. I have just written one more page here. Just observe this.